these first handful of questions that we've done here have all had a really similar theme, but we'll get into some different themes here, I think, today. Just some different strategies on how to create these. Like a general strategy for how you constructed this? Substitution. Now, there's some really good foundational things to talk about. Because couldn't you have done, I want you to get this, couldn't your strategy have been this, and maybe some of you did this, you could have looked for the centering point and realized there is no centering point, right? At least none given. And so you're kind of left with like, wow, what do I do? Maybe you arrive at I do know the series for cosine, and so maybe I could do what was suggested and just substitute into that, right? Given the stuff that I'm supposed to know, that would be a great strategy. So maybe we could write f of x equals, and then wherever you see an x, we would substitute a root x, right? So this comes down to, I think you're all probably really, really good at substituting, but it really comes down to, did you remember, or do you remember, the power series for cosine of x, right? So I don't know, maybe you want to write that down. Maybe that'd be maybe you did do that. Cosine of x is approximated by 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial plus dot, 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 x to the 2n over 2n quantity factorial. Maybe you start there. I think it would probably be a great idea to write that down just as an attempt to help you memorize it. And then you substitute. Cosine of root x is approximated by 1 minus, of course, root x squared is what? X, so you could just write x over 2 factorial plus, it would be x to the what? X squared over 4 factorial minus x to the 3rd over 6 factorial, there we go, plus dot, 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 plus, what would that nth term look like? X to the n, right? Because the square root of x to the 2n, the 1/2 for the square root, we would just multiply the 2 but get a 1, right? The x to the n over, yep, we'll get there, 2n factorial, right? And then it is alternating, and what would the alternating element look like? Oh, I forgot it up here too, didn't I? There we go. And does that alternating element change for this one, or is it the same? It wasn't affected at all, right? So negative 1 to the n for the alternating element. Okay. What do you guys think? What do you think about the interval of convergence? Let's start here. What would be the interval of convergence for just cosine of x's power series? Yep. Negative infinity to positive infinity. And then what do you think would be the interval of convergence for our power series for cosine of root x? Johnny?
Something to infinity, somewhere. It probably either including 0 or excluding 0, but it can't be negative.
But no negatives? Why? Okay. What do you guys think of that? Any thoughts? Dylan?
I think is it still negative infinity to infinity? Because like you can still substitute in all the negative numbers and x to the n. Like it doesn't change.
So the question is, though, like the question we're trying, like I think we probably would all agree that you're allowed to plug as many negative numbers into that right side as you would ever want. The question is, though, if you did, would that be equivalent to cosine of root of those negative numbers? Does that make sense? Johnny, you wanted to add?
Yeah, so just like in the original domain of whenever we have anything previous, like integral or something like that, or like differentiable, we always have to like take account of domain, so
Right.
I do think it'd be the same thing here. So like you could include the original domain before you mess with anything.
So think about it like this. What if did we not, to go from here to here, did we not just substitute root x wherever you saw an x? What's to prevent us from doing that in the domain as well? You absolutely can do that. So check this out. Up here, the domain, the interval of convergence was negative infinity to infinity. So how about this? What if I said negative infinity is less than root x, which is less than infinity? Let me do a little better job with that infinity. Right? So, gets into this weird conundrum, right? Because if you're going to solve for x, what do you have to do? Square both sides. Square both sides. And so, what's a negative gigantic number times a negative gigantic number? No. Negative times negative is a positive, right? And so I think we're forced to look at this kind of from Johnny's perspective and say, well, gosh, we're allowed to plug all the negative numbers we want into that right side, but will that actually be equivalent to plugging in negative numbers into the left side? And I say, no. Cosine of root x, I mean, you could graph that, right? Cosine of root x. I'm pretty sure that you'd find that to the left of the origin, there's nothing there. At least not with real numbers, right? Hey, cool. So for at least real numbers, I think for this one, we'd be forced to say x 0. Yeah. Come on. There we go. 0 is less than x, which is less than infinity, with a possible closed on the left end. Right? Possible closed on the left end. And I think you're definitely going to get it closed on the left end. I don't know if I have room to fit this in down here, but I think if you plug a 0, in, you just get 0, which converges to 0, right? So I think we'd probably put a closed on that. I bring this up. This is kind of a trickier one, right? Because you have to reason through a little bit. It's not quite so mechanical. Anyways, we'll do a few more of these intervals of convergence for sure. Definitely a trickier one. Okay. Comments, questions, concerns? I'm really excited about the next one, number 5. So number 5 has 2 parts. Let's for sure do the first part. I think the first part will be relatively straightforward based on what we've been doing. And the second little bullet point, which I think is on the next page over, we'll see. Probably pretty straightforward too. We'll see how it goes. So please try number 5. Question. I was like, I looked at my little note on my little 3x5 card, and I had the exact right answer, and I wrote the wrong answer, and I was like, whatever. Who knows? Anyways, sure. And then, did you have an nth term?
I said -1 to the n times x to the 2n over n factorial.
What do y'all think about that? Looks pretty good. Agreed. What do you guys think about the interval of convergence? What do you think it ought to be? It's got you choked up, doesn't it? Negative infinity to infinity. What do you guys think of that? I think it's right. It's good. Okay. Very good. Plus or minus infinity.
Well, no, it's actually plus or minus the square root of negative infinity plus minus the square root of infinity.
Oh, you got to get the I in there too, right?
Yeah.
Got to get some complex. Anyways, it's good. Makes sense.
I mean, yeah.
All right. So then, this next piece is pretty sweet because if you look at this, and for just a moment you like stop being a calculus student and you just be like a mathematician, and you start to ask yourself, well, what techniques do I have for finding that antiderivative short of just doing math 9. I have no real techniques to do this, do I? E to the negative x squared. Well, if it was going to be a Timmy messed it up, wouldn't there need to be another factor in there that's like x, something x, right? If there were, we could substitute that right away and be pretty easy. I think you'd find if you tried integration by parts, similarly you'd get stuck. You'd get into that death spiral of integration by parts and realize you're not making things better, you're making things worse. And so we don't really have a good technique for doing this other than what we're about to do. We're trying to find this definite integral from 0 to 1, and I don't have a clue what the antiderivative is, but I do have a good idea of what the approximate polynomial would be for e to the negative x squared. And so what this says is use the first 4 terms that we just found to approximate the value of that definite integral. And then not only that, we got to acknowledge that we're off, and we want to bound the error and say, this is my answer, my best answer, and this is how far off I could be. Does that make sense? So I want you guys to explore with this a little bit. You got the power series right there in front of you. See if you can use that strategy to try to answer a question that obviously up to this point would have been totally impossible, other than Math 9. Believe it or not, your calculator is using a special form of a power series to do Math 9. So I'm just asking you to kind of figure out what the calculator is doing a little bit. Okay, let me see if we match up. Let's check this out. First thing I'm going to say is that the integral from 0 to 1 of e to the negative x squared dx is approximated by the integral from 0 to 1 of that power series that we just came up with, right? So it was, 1 minus x squared plus x to the 4th over 2 factorial minus x to the 6th over 3 factorial dx. Does that make sense? Excuse me, sorry. Okay, so if that's true, then the whole point of this kind of is that it's really easy to find the antiderivative of a polynomial. So I'm going to do that next. So the antiderivative, bless you, would be x minus 1/3 x cubed plus 1/10 x to the 5th, if you multiply out there. And then it would be minus 1/42 x to the 7th, I think. Evaluated from 0 to 1. Still making sense? Okay, so then to finish it off, we need to plug in the 1 and the 0 and do the fundamental thermal calculus. Part 1, we find the difference in the evaluations. So you can see another kind of a side benefit to this is with a polynomial, when you start plugging in zeros, usually you just end up with 0, right? That's kind of nice. So if I do plug in the 1, I get, I'll put this, I'll just say is approximately equal to, it'd be 1 minus 1/3 plus 1/10 minus 1/42. Still making sense? And so we could simplify that. The common denominator, golly, I don't know what that is.
That's not
420 for sure. Maybe there's something smaller than 420, but you could add them all up. And 210 work? I guess 210 works. You could add them all up and get some number, right? Did anybody do that?
No.
Is that? Oh, your calculator. Okay. 26/35. We'll trust that that's right. Perhaps someone watching the video later will say, no, it's this. You can tell us. But anyways, So assuming that we've added those up correctly, this would be my approximate value for this definite integral. Let's also bound the error. So I'll say that the absolute value of the integral from 0 to 1 of e to the negative x squared dx minus 26/35 is bounded by what? Why would I use the first neglected term as my error bound? Yay, and not just an alternating series, but a converging alternating series. There you go. So we want to put that in there and say something like, because it's a converging alternating series, the error bound, I'll just put BD for bound, is the first neglected term. So you want to write that, actually want to write that out. That's your reasoning. Otherwise, it just seems random. Let's just use the first neglected term. Here's why, right? It's a converging alternating series. Error is bounded by that. So what is the first neglected term? What would have come next if we went past the 1 over 42?
1 over 216.
1 over 216? Let's see here. So it would have been x to the 8th over 4 factorial. So it'd be 8 times 24, or 9 times 24 because you're adding. So 180 through to 216 makes sense. Sure. Okay. So the next first neglected term would be 1 over 216. And so my error is bounded by that. That'd be the max that I would be off. So if you wanted to, you could even kind of test out your Math 9 on your calculator. You could do Math 9 on this thing and then subtract 26/35 from it and see if that actual, maybe even a better expression for error, is less than 1 over 216. That make sense? You have to test it out and say, hey, is my calculator really showing that the error is less than that? And I think that you probably would. What if 1 over 216 was too big of an error? What would we do? Cry and then put more terms on the series, and then I think we'd be able to decrease the error quite a bit, as much as we want. Okay. Questions, concerns? This is a big deal, right? This is one of the chief aims of what we're doing here. All right. So we're going to shift gears a little bit. Why don't you take a look at number 6? A little bit of a gear shift here. Yep. Write the first 4 terms and the general term for the power series x over 1 minus x. Include the interval of convergence. So give this one a shot. Has anybody figured out that substitution is not the magic pill here? Have you come up with anything?
No.
Would you multiply?
Say again?
Would you like to multiply by x?
Let's see if that works. So Jasmine suggested we multiply something by x. So Jasmine, let's be really clear. Like what exactly am I going to be multiplying by x? What do I start with?
1 plus x squared.
Because that's the same thing as,
Geometric.
yeah. So if you started off with that, let's see if Jasmine's idea of multiplication works. And I would highly recommend that, like I'm doing here, that you also, if you're going to start off with one of these, write it down. That will aid your memorization of it. So that's why I'm writing it down. So you said multiply by x. So let's see what happens. If I follow the rules for equations, which say if you multiply the left side by something, then you have to multiply the right side by the same thing. Let's see how this goes. So on the left side, I don't think anybody can argue with the idea that on the left side, we have exactly what we were tasked with finding, right? X over 1 minus x. On the right side, let's see if this causes any issues. What would my nth term be if I did what Jasmine said? Yep, x to the n plus 1. What do you think? Is there an issue there? Have we broken any math rules? I think she's got it. It is multiplication. Yeah. Were you guys thinking the same thing? Yeah. Totally right. I think this is exactly right. Sometimes you fall into that trap of like, it should be way more difficult than this. So let's see here. The nth term looks good. What do you guys think the interval of convergence for this would be? Any ideas?
Negative x.
Well, the original interval of convergence for the geometric series is from where to where? Negative 1 to 1. And I don't know. You could go back through and do a full ratio test and all that stuff. I don't know. Pretty sure you're just going to get negative 1 to 1 again. I don't think it's going to affect the endpoints at all. Yeah. Practice that if you so choose.
Now, I need the substitution
It's possible. What'd you substitute?
of 2 minus 1 over x.
2 minus 1 over x.
Which gave me 1 over x minus 1. So then you would multiply both the top and the bottom by x.
Yeah.
You substitute it in. Would that be a viable solution?
So the only issue, so you've changed the centering point.
So then I would plug it in to change my interval of convergence.
You'd plug what in?
2 minus 1 over x. So basically that.
Oh, for your interval? Whew.
It's a lot of extra work.
Let me think about that one. I can say for sure that your strategy might be really interesting in 7. Of like this. Basically, what comes down to, you did 2 steps. You substituted something, and then you multiplied by something. I think that strategy is going to be really interesting in the next couple of examples. Let me do some thinking about 6 real quick. Okay, let's finish off with number 7. I'll give you just some time to explore number 7 a little bit, and then, like I said, we'll finish off with this one. So, yes, sir.
What was the interval convergence for?
Negative 1 to 1. Okay, please, Liz, just go with me here
Suspend your disbelief.
for a little while.
It's pissing all over him.
Okay, so guys, I think that there's 2 really distinct ways to do this. I want to show you both. Here's the first one. I might look at this. I might look at this over here and see some kind of a very modified geometric series, right? Certainly not cosine, sine, or e. If it's anything, it's going to be this geometric. So I might start off with this and say, well, if this is where I'm starting, I got a lot of work to do. What do I need to do? So I think that there are 2 pretty distinct operations going on here. Would you agree with me that the x has been replaced with x squared? At least in that, if you compare these 2 red highlights, obviously x has been replaced with x squared. Is it frozen again? I thought I unfroze it. Unfreeze. There we go. I must have double hit it. That make sense? You see the 2 red highlights now? Okay. But then the numerator, would you guys agree with me that the numerator appears to have been multiplied by something kind of like the previous one? So this is kind of the first combination of things that we've seen. So I'm going to give you a hint about something. If you ever look at one of these and you think, wow, something has been substituted in and then something has been multiplied in there, you always want to cover the substitution first. Cover the substitution change first, simply because if you do the multiplication first, when you do your substitution, you need to substitute into that too. So substitute first, then multiply. So here's what this could look like. I could say over 1 minus x squared would be approximated by 1 plus x squared plus x to the 4th plus x to the 5th plus ... plus x to the, or so it'd be x to the 2n, I guess. Yeah. And then do you see the multiplication coming up? I could multiply both sides by 1 plus x. So it would be 1 plus x times all that stuff. And I think you'll find kind of a curious result. I'll just leave off the nth term for the moment. How about that? You'll find kind of a curious result because when you actually distribute this and start multiplying, wouldn't you get 1 times everything and then x times everything? So 1 times everything would just be 1 plus x squared plus x to the 4th. Oh, gosh, it should be... What am I doing? Let's go with 6. There we go. Now all those weird looks you were giving me make sense. Okay, plus, that'd be x to the 6th, plus ... But then you got to still distribute the x, don't you? Okay, so then when you distribute the x, you get x times 1, x times x squared, x times x to the 4th, x times x to the 6th. And you start to realize, whoa, no matter how many terms I write out here, aren't I going to just be getting all of my odd degreed terms back? And so this would be really weird because if you rearrange things the way they're supposed to be in ascending order, you'd get a really curious result because you get this. And why is this so interesting? That's what we started with, isn't it? Like, doesn't this match this? Exactly. And so you might go back and say, like, hesitantly, you might say, well, does that mean that too? And, like, are these really the same? You know, I don't totally understand, but there is something to understand, isn't there? What is it, Jeff?
Do like the difference of square in the denominator?
Oh, we could have done that at the start, huh? We could have said, well, instead of going through all that work, we could have just said 1 plus x over 1 minus x squared is really 1 plus x over 1 minus x times 1 plus x. This would cancel with this, wouldn't it? Leaving you with 1 over 1 minus x, which is the series that you already are supposed to know. So you'd say, well, that's approximately equal to 1 plus x plus x squared plus x cubed plus ... plus x to the n. So the reason why that's in there is I want you to get more and more comfortable with the idea that you can manipulate these series using all the regular rules of algebra, as long as you actually use those rules of algebra. There's a lot of manipulation that can happen. This is just a nice example of if someone recognized it, it would have been over with in like 15 seconds. And if you didn't, it could have taken you longer. So be aware, you can manipulate these things a lot. Go ahead.
So we don't have to like write all those stuff, we can just say like
No.
y is the same
You honestly could have just done the stuff in red. Yep. I just thought I'd show you both just so you can see how highly manipulable they are. So. All right, wonderful. We're on track. We'll keep practicing next time. See you guys.